Assalamualaikum. Today's video lesson is another problem on the kinematics of a projectile body, such as a test rocket launched from an incline and follow a parabolic path under the influence of gravity alone. So hang on till the end of this lesson. Watch and learn. Question is, a test rocket starting from rest at point A is launched by accelerating it along a 200.0 meter incline at an acceleration 1.90 meters per second squared. The incline rises at 35.0 degrees above the horizontal, and at the instant the rocket leaves it, the engines turned off and the rocket is subject to gravity only. Ignore air resistance. Find letter A, the maximum height above the ground that the rocket reaches, and question letter B, the rocket's greatest horizontal range beyond point A. The rocket is launched initially from rest, so the initial speed v0 is equal to 0, and the rocket accelerates at 1.90 meters per second squared along this incline or ramp, whose length is given as 200.0 meters, and the angle of inclination is 35.0 degrees. Our first target variable in part A is the maximum height, denoted here by capital H max. So in our diagram, this maximum height refers to the greatest vertical distance, okay, that is reached by the rocket as measured from the ground. And in part B, we are also required to determine the maximum range. All right. When you say maximum range, denoted by capital R max, we are referring to the sum of the horizontal distances, denoted here by D. D is the length of the base of the ramp, and capital R is the horizontal distance traveled by the rocket, right, as it moves from point B to point C. Point B and point C are at the same level. All right. So when the rocket reaches point C, it still has to travel downward along this parabolic path. So there is still an additional horizontal distance labeled here as X. Right? So R max is the sum of those distances, D, R, and X. The computations starts with determining the final speed of the rocket as it leaves the top edge of the ramp. And we use the kinematics formula. V is equal to the square root of twice the acceleration A multiplied by the length of the ramp, capital L. That is, the final speed V as the rocket leaves the ramp is square root of 2 times 1.90 meter per second squared and multiplied by 200.0 meters. That is, the value of the final speed v, right, is 27.6 meters per second. Right. Now, when the rocket leaves the edge of the ramp, okay, the engines of the rocket are off. So in other words, the subsequent motion of the rocket will now be a projectile motion. So 27.6 meters per second, therefore, becomes its initial velocity, all right, with the same magnitude, 27.6 meter per second, and with the direction represented by the angle 35.0 degrees above the horizontal line, right? So the horizontal line connecting the 2 points B and C, right? B and C are at the same level, right? And since what we want is how far will the rocket be able to reach, right? Beyond this horizontal line. And to find that height, we use this derived formula. That is, capital H is equal to v squared. This is the initial velocity, all right, which you just computed earlier, 27.6 meter per second. That will be squared, and then multiply it by the square of the sine value of the angle theta, or 35.0 degrees, and then divide it by twice the acceleration due to gravity. So substituting the quantities into this formula, we have capital H is equal to the square of 27.6 meters per second multiplied by the square of the sine of 35 degrees and then divided by 19.6 meters per second. So when you do our math, we find the height h equal to 12.8 meters in three significant figures. Take note, this is not yet the maximum height from the ground, but rather it is just the maximum height, okay, from the horizontal distance connecting point B and point C, right? The vertical height of the ramp, which is labeled here as small letter h, can be determined by simply multiplying the length of the ramp, which is 200.0 meters, by the sine value of 35 degrees, right? This is based on the definition of the sine of the angle theta, okay? Uh, the vertical height, small letter h, happens to be the opposite side of that angle. And the length L happens to be the hypotenuse. Since what we are after is the vertical height h, then we just multiply the length of the ramp and the angle or sine value of the angle 35 degrees, which with the help of your cycle, we get the value of the height small h equal to 115 meters. And so therefore, we can now determine the maximum height reached by the rocket measured from the ground. That is simply the sum of capital H, or 12.8 meters, plus the value of small h, 115 meters, for a total of 128 meters. And this is our answer to question letter A. In the case of the horizontal uh, distance or range of the rocket, we can use the formula, also a derived formula, to determine the distance from point B to point C, which we label here as big R, right? So big R is equal to the square of the initial velocity at point B and multiplied by the sine value of twice the angle, right? Divided by G. Notice the difference in this formula for determining the range from that of determining the maximum height. All right. The meaning of sine 2 theta is that before determining the sine value of the angle, we first multiply the given angle by 2. All right. Or big R is equal to the initial velocity, 27.6 meter per second, then square it, and then multiply it by the sine of the angle 2 times 35.0 degrees, which is 70.0 degrees. So after getting the sine of 70.0 degrees, that's the time that we can do the next operation, which is we multiply that value of the sine of 70.0 degrees by the square of 27.6 meter per second before we divide the whole thing by 9.80 meters per second squared. So again, with the help of your cycle, we find the value of big R equal to 73.0 meters. All right. Take note that is just the value of the big R, or the horizontal distance from point B to point C. Right? Now, the length of the base of the ramp, which is labeled here as small letter D, okay, can be determined again using the definition of cosine of 35.0 degrees. Right? This small d, or the distance corresponding to the length of the base, okay, happens to be the adjacent side of the angle. Right? So the ratio of that adjacent side to the hypotenuse, or the length of the ramp, is actually equal to cosine 35.0 degrees. That's why we can find the distance small d, okay, by just multiplying 200.0 meters and the cosine of 35.0 degrees, which of course is equal to 164 meters. When the rocket reaches the point labeled as C here, it's going to have the same downward or magnitude of the downward velocity, all right, which we denote here as b sub y. And that downward component of the velocity is just the product of the velocity b and sine of the angle theta. That is 27.6 meters per second multiplied by sine of the angle 35.0 degrees, right? So the direction of this y component of the velocity, of course, is downward. And its horizontal component is directed to the right. But right now, we have also the value for this y component equal to 15.8 meters per second. And the x component of v is, of course, just the value of v multiplied by cosine of the angle. That is 27.6 meters per second times the cosine of 35.0 degrees, or again using your cycle, we get the value Vx equals 22.6 meters per second, and the direction is to the right. So when the rocket reaches point C, its instantaneous velocity, okay, is just the same as its the magnitude of its velocity at point B, right? And our last task is actually to determine the value of the horizontal distance labeled here as x, all right? Since we don't know what the final component of the velocity is, it's not given, but we know the height is small letter h. So the appropriate formula that we can use is the kinematics formula, okay, expressing that height h. That is, that height h, or small h, is equal to b sub yt plus 1 half gt squared, right? So our task is to determine the time t, the time it takes for the rocket, all right, to move from point C to point D, or the ground. And doing that, we have to treat the quantities, the velocity and the acceleration, as well as the displacement, as vector quantities, right? Which means that the height small h will be considered negative, all right? Because relative to point C, which is the reference, the ground happens to be negative 115 meters, or 115 meters below point C. And then we equate that to the value of um, the y component of v, which we earlier computed, equal to 15.8 meters per second. But since it's directed downward, we put here the negative sign. And then that is multiplied by the unknown variable t. And then plus 1 half gt squared. G is treated as a vector, so it's negative. And 1 half of 9.8 meters per second squared is equal to negative 4.9 meters per second squared, also multiplied by the square of the time t. So simplifying this equation, we will come up with a quadratic equation written in standard form. That is t squared plus 3.22t minus 23.5 equals 0, right? And if you're going to apply your quadratic formula, right, we will be able to arrive at the more appropriate value for the time t. As you may all know, uh, simplifying this quadratic equation will actually lead you to two answers for t. One is positive and the other is negative. So we take the positive value of the time t, which is more appropriate in this situation. All right? And that value of the time t actually is equal to 3.49 seconds. And using that time t, we can proceed in computing the value of the distance x. All right? Simply equal to the product of the x component of the velocity, which we also have computed earlier, all right? And then multiply it by the computed time. That is 22.6 meter per second multiplied by 3.49 seconds. We will arrive at the value of x equal to 78.9 meters, right? So finally, our answer to question letter B, what is the maximum or greatest range acquired by the rocket measured from point A? Our answer is 164 meters plus 73.0 meters plus 78.9 meters for a total of 316 meters in three significant figures, right? Our diagram here is not quite accurate because it appears that the value of big R, right? The value of big R is only 73.0 meters, while the value of X, okay, is 78.9 meters. What I'm saying is the way this diagram is drawn, okay, the distance d, all right, the distance r and the distance x are not drawn to correct scale, right? So this is our answer to question letter B, and that concludes our video lesson for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for your indulgence. Please don't forget to subscribe